Good morning, good afternoon, good evening, wherever you are on this planet Earth, and welcome to our SETI Live. My name is Franck Marchis, and I'm a Director of Citizen Science at the SETI Institute and at Unistellar. And here with me, Sgro. Hi, Lauren.
Yes. Hi, Frank. It's very nice to be here today. I am the exoplanet lead astronomer for the SETI Institute and Unistellar's Citizen Science Network. So today, we're going to answer some of your questions and talk about the latest and greatest in citizen science.
So we're going to talk specifically about citizen science at Unistellar, our network of telescopes. You can see some of them in the background in case you don't know what we are talking about. So those are telescopes that you can find in stores. You buy them and you enjoy the dark sky, and you can do also science, help researchers at the SETI Institute and elsewhere to discover phenomena.
The great unknown.
The great unknown.
Yes.
Yeah, that's a good one. All right. So talking about the great unknown, you went to New Mexico, I heard.
I did. I went to New Mexico.
I saw the bills.
Yes. So there was a conference on long period exoplanet transits, which is something that we are really good at dealing with the Unistellar network. I was able to attend and kind of learn about where the community is in their studies. And I also got to meet what we call Team New Mexico, which is a group of citizen astronomers in New Mexico. Hi, Margaret, Karen, Michael, Lydia, if you're watching. I was going to show a picture of our great dinner, one of the bills that Franck is talking about.
So in the meantime, I'm going to explain that if you hear some noise in the background right now, it's because the SETI communication team is coming to visit us today. So you're going to hear people passing by and dogs barking because we have a dog in the office.
Yes.
So
Stormy.
So you went to see them. You talk about what?
What did we talk about?
Yeah.
We talked about everything. We talked about what got us interested in astronomy. We talked about how to improve the citizen science network, the observations that they were taking, and how they've kind of formed their own little community, which is really great. It's one of the amazing parts of what we get to facilitate in this work. So they were all super fun. Sorry, I need to zoom in on this picture, but we had oh, no, it's not working. But we had a blast. Okay. It was fantastic.
Yeah, so if you are somewhere on this planet, follow us on social media. Sometimes we go to different places, and if you want to meet us, that's possible. For instance, I'm going to Puerto Rico in 10 days, and I'm going to meet some people over there. And I'm going to Helsinki with Ariel and Peter. We are going to attend a conference called DPS-EPSC, and we hope to see some of our citizen scientists over there.
We do have a few.
Yeah, we have a few. We have the Peters.
Yeah.
We have people in the Baltic as well. It's not far away. So tell us when you follow us on social media, and if by chance we are nearby, let us know. We can have a dinner and meet you in person.
Yeah.
So you'd probably talk about some kind of cool new projects that we did, and let's go to one of them, Comet 3i Atlas.
Yes, exactly. Our new interstellar visitor.
So everybody knows about that, right? I'm assuming. If you don't, let us know. But frankly, I'm sure you know that we discovered recently, the community of astronomers, specifically using an instrument, Atlas telescope, discover a comet, and the orbit of the comet. The orbit of the comet shows that it's coming from the outer part of the solar system, from outside of our solar system. It's an extremely fast body. It's not the first time we have been visited by an interstellar object. The first one was Oumuamua in 2017, and then we have Borisov in 2019, and now we have 3i Atlas, which is also C 2025N1 that was discovered in July 1st, 2025, so quite recently, from Chile. So he has a very interesting orbit. I don't know if you can show the orbit.
I'm about to.
You can about to. He has this hyperbolic orbit, meaning that he's coming to the solar system. It's gonna leave. Okay, it's extremely fast, extremely eccentric as well, and it's moving faster than any of the interstellar bodies we have seen so far. So that's a very cool object. So why do we care about that? Well, because this is coming from another solar system, another planetary system. So we have an opportunity to study and to understand the composition of a body that's coming from another planetary system. You know, planets' waveform have been formed from these comets and asteroids in the past. So here we have a fragment of another planetary system coming to us. When we discovered Oumuamua in 2017, it was too late. For Borisov, we had done some observation with the campaign, so we have some better idea of the composition of the body. For this one, we discovered so early that we're really truly going to be able to get a lot of information. So the first question we had is it possible to observe it using our Unistellar telescope? And why? So yes, we can observe it. In fact, this has been confirmed like 4 weeks ago, if I remember. Mm-hmm. We have observation collected by multiple citizen astronomers. I think we have 25 or 30 of them or something like this at the moment.
If not much more, yeah.
We can count them later. So this is an observation by Ian Transom. I think Ian is in New Zealand or...
I think he's in Australia.
Australia, okay. And we have another observation, maybe, I don't know if I've uploaded this one. So we have collected multiple observations. And if you see, on this image, you see a tiny dot and some lines nearby. The lines are the stars because we are analyzing by taking observation on the object and we stack the observation on the object, meaning that the object, since it's moving with respect to the star, you see the star as a line and the object as a dot. So what do we care about observing a dot? It's not that interesting, right? You will say. What do you think? Is it interesting to observe a dot?
It's interesting to me to observe a dot because that's pretty much our entire job. Yes, exactly. But it is interesting to observe these dots because by observing them and essentially taking the change in brightness over the course of an observation or over the course of the time, we can track how the comet in this case is changing. We can track its activity because as comets vary in their orbit, their location to the sun, we see them get brighter or dimmer.
Yeah. So we're gonna show you that. So from a dot, we measure the flux, we measure the position. So we refine the orbit of the comet, and from the flux, we have an idea how the comet activity increase. Because as the object is coming closer to the sun, is getting into the warmest part of the solar system. So this material that is made of, which we believe is still a mixture of ice and rock, is vaporizing slowly. And this increases the brightness. So that's not theoretical. We see that for a lot of comets, and we see that also for this interstellar comet. So this is a figure showing at the bottom the name of everybody that made an observation of this interstellar comet. So it's more than 30, definitely.
Yeah, it's definitely more than 30.
You can count them if you have time, but there is a lot of people in our community that did observation of this interstellar comet, probably more than 50. And so the gray dot are data that we did not use for this figure because the observations were taken when the comet was close to a star. And in this case, it's very difficult to extract the photometry, the flux of measure the flux, the brightness of the object. But in the color dots are basically the one for which we could extract a good measurement of the comet brightness. And this is done by Ariel Grekowski, our lead in cometary activity.
And actually, I think that Ariel was talking about this in another SETI Live, but like what Franck was talking about, extracting that brightness, the first observation that we had of this comet where we definitely detected it was a record for the Unistellar network of the faintest object that we had ever detected. It was 17.8 magnitude, which is very, very faint. If you don't know what that number means, I can assure you it's very faint. So we've actually been able to watch it get brighter, as you can see with the trend on the graph over this course of time. And we expect it to get its brightest this fall. However, this fall, it's going to be too close to the sun to observe, I think, for a little bit. So we have to get all the observations that we can right now. Yeah.
So the goal is to put all these measurements and to kind of estimate, do a model of the comet variation, light variation. That's the blue line you see here. You may be able to see it with the pointer. I don't know if it works. And this blue line basically is predicting the brightness of the comet when it will be close to the sun and close to us. And that's typically, in this case, magnitude 14. Okay, so quite bright for an object observed with a unistellar telescope, because we can go much deeper in brightness. So this is cool because it's an independent measurement of the brightness of the comet from an independent group. We are only unistellar data. And the measurement we got, the prediction we got, is basically in agreement with JPL observation and another group of COPS. Thank you. So this is the kind of science we can do. And the reason we want you to observe more this comet in the future is because we want to refine this line. It's going to get brighter, better. And more importantly, we may see some weird things happening. So what kind of weird stuff a comet can do?
Comets can outburst, for one. So essentially, as the ices maybe underneath the surface or on the surface get really heated up, they all sublimate at the same time. And that increases the brightness usually dramatically. And it's really going to be interesting to watch the activity of this comet, because we know how comets from the solar system, we know how those usually change in activity in their orbit, but not so much for these interstellar comets. So it's going to be, like Franck said, really interesting to see exactly what it does.
Okay, before we go to the other object, if you have any questions, don't forget you can ask questions. So we're going to take some time to answer to them. But let me say hi to people watching us from Normandy. You know why I care about Normandy?
Tell me why you care about Normandy.
I was born there.
No way.
Very few people know that. I was born in Caen.
Pretty cool.
Okay, and then
I'm gonna remember that.
And then Texas, Tyler, Texas, and Quebec, Canada, Parsbesbiak. Okay, Plainville, Minnesota, I believe it is. Netherlands. More people from France, from California, from Vienna. Hello, Mario. From Germany, from
First citizen astronomer.
We have some citizen astronomer.
Oh, there's my mom.
There's Ariel. You have a mom.
Hi, everyone.
We invited the entire family.
Okay.
And yeah, thank you. So we are talking about the citizen science. We have been some research in citizen science we have done over the past 2 months. So we talk about Comet.
Yeah.
The comets are amazing. I agree with that. But there is some very cool stuff we can do with the Unistellar telescope, and that's detection exoplanet.
Yes.
And more importantly, not whatever exoplanet, we can observe disintegrating exoplanet.
Yeah.
So we have the specialist of exoplanet here, and she's going to tell us everything about
disintegrating exoplanet. I'm going to tell you everything I know.
All right, go ahead.
So disintegrating exoplanets, I don't know if you've ever heard of that. It is a very interesting and rare phenomenon, but there is one that has been discovered recently, this past May, actually. So really recent discovery. It's BD plus 054868.
Wow, what an amazing name.
I know, we should really get better at naming things. But this exoplanet is one of only 4 disintegrating planets known. It's the 4th discovery, and it's a Mercury-sized planet orbiting a star that's cooler and smaller than our sun. The interesting thing about it is that an Earth-Sun distance is what we refer to as an AU. This planet is orbiting only 0.02 AU from its host star, meaning that it gets really, really close, and it orbits very quickly because it's so close. It only takes about a day and a half for this planet to orbit. Now, we expect that this is a rocky planet, and because it's so close to its star, it is actually actively disintegrating. Its star is basically melting it in real time. And as the planet transits, which is really cool, this is a planet that transits and we get to observe that, the disintegrating material is essentially creating a tail like a comet would. So I'm going to show you.
Let me, while you're doing this, I'm going to explain. So basically, when you observe a transiting exoplanet, generally you see a very boring light curve where you can see a small attenuation, a plateau, and then an increase. Okay, it's boring. It's interesting, but it's boring for most people. But when you observe a disintegrating exoplanet, because the exoplanet has some kind of tail, oh my God, it's a comet at the end.
Everything goes back to the comet.
It's always a comet, right? Ariel agree with us. It's always a comet. So it's a gigantic comet with a lot of material ejected, basically, because it's a big planet, the size of...
It's Mercury size.
Mercury size. Kind of a small planet, but okay, it's a planet. So it's a rocky Mercury-like planet, fragmenting and ejecting fragment, becoming a big comet. And this is the light curve you see in this case.
Exactly. So this is from TESS data. TESS is NASA's Transiting Exoplanet Survey satellite. And you can see in the leftmost part of the plot where we're only receiving the light from the star, essentially. And then as the planet passes in front, you see a really dramatic drop in that star's light because some of that light is getting blocked. The interesting part is that as the planet passes in front of the star, usually we would see a similar trend on the exit of the exoplanet in its transit. But instead, we see this really gradual increase in brightness because the planet is passing in front of the star, and then the tail is passing in front of the star. So everything in that right part of the plot that you see here, the measurement of light over time, is this tail passing in front of the star and that tail blocking the star's light. So that's what makes this particular light curve really interesting. That's how this planet was discovered, was seeing this type of trend in the TESS data. Astronomers knew that something interesting was going on.
Very cool. So we don't know many of those. Why?
We don't know many of those because we, first of all, assume that they're quite rare. A planet has to transit, for one, and it has to also be close enough to its star and be actively disintegrating. We just don't see this type of trend in light curves very often.
So do we know why this planet is disintegrating?
Why it's disintegrating?
Yeah.
Just because it is so very close to its star and because it's a pretty small planet. So if it was a larger planet, its surface gravity may be able to keep everything intact. But because it's just a Mercury-sized planet, it doesn't have enough mass, it doesn't have enough gravity to keep it from being ripped apart by its star, basically.
Oh, okay. So it's basically entering into the area, the Hill sphere.
Exactly.
That's what you call, right?
Yes, exactly.
I didn't forget everything.
Oh,
yet.
man.
It's amazing. So you enter in this area called the Hill sphere, that if you have the cohesion of a rock, typically there is some kind of internal cohesion. If you enter in the Hill sphere, the stretch from the side which is close to the sun to the side which is away from the sun is bigger than the cohesion, so you start losing pieces.
It starts getting ripped apart. It's not stable anymore.
It's not a nice way to
I'm
die
so proud of you.
I know. It's
exoplanets after.
So I don't only write proposals, I also have some memories about things.
He does.
Okay. So that's very cool. And so how many times we observe this transiting exoplanet?
So now this is going to be pretty cool, I think at least. So we were contacted by a group that is observing this exoplanet with the Keck telescope in Hawaii. They essentially want to measure what the planet is made of. They're trying to get spectroscopy so that they can essentially look at what the tail itself is made of, because that tail is coming directly from the planet. It's essentially melted planet. So by looking at its contents, we can actually tell what this planet is made of, and that's a view that we typically don't get. We can usually only, look at planetary atmospheres, but this time we can kind of look at the interior of the planet, its contents, by observing the tail. So they contacted us because at the same time that the professional telescope is observing the planet, they want to be able to know exactly where in the transit we are. And in order to see where we're at in the transit, we need a massive telescope network that can catch the entire transit.
So massive in a way that it's distributed.
Distributed, yes. Longitudinal
that's
coverage.
decentralization.
Yes,
we're going to talk about that in the future. So that's the reason I wanted to say the word distributed.
Exactly. Got it. I'm filing that.
Not big in size. A telescope, it doesn't matter if it's like 3 meters.
This is very true.
What's matter is that we have plenty of them.
Expansive, global.
Okay.
Yeah.
So
because we have a global network, we were able to catch the entire transit. Now, Keck is just one telescope. It can't catch the whole thing because the transit is 18 hours long. So we had a almost 22-hour observing window that we needed to gather observations over to catch this transit at the end of July. And we actually set a record. I just looked into the data this morning and recognized we have 26 hours of continuous coverage on this planet.
So we're going to show you a figure that basically show the data being sent to us recently. And the one in which one is you call
Pink.
Pink are the transiting exoplanets. What a surprise. And
I actually didn't decide that.
Yeah, well, that's a good choice, I think, because you can see it, right? There was a lot of them taken in the United States on this video.
And this was only part of this video only covers part of
So how many people observed this?
We had about 26 observers and 26 hours of continuous data. They actually observed longer than we needed, which is perfect. But this sets a record for us. We've never had that long of a continuous observation. It is full coverage.
So we are going to soon be able to show a Likert, I'm assuming.
Yes.
You're working on it?
I'm working on it. I'm working on it. And he saw a little bit of it this morning. So I'm trying to get into the data. It's because it's so much data that it just takes a little bit of time to go through.
And we have the data coming now because the last one, the last transit was 2 days ago?
Yeah, it was Tuesday night for us. So August 13th and 14th, we had a second chance to observe this planet, and we'll actually have 2 more chances to. Before
we talk about this, let me just clarify, because people often ask this: how much data you receive every time someone observes a transiting exoplanet? How many frames? What's the size of this?
Yeah, it's actually for a typical few hour transit. The raw frames, it's usually 3,000 to 5,000 raw frames, and about maybe 40 to 50 gigs of data.
Okay. So imagine this coming on our servers every 5 minutes from all of you around the planet.
It's a lot.
And we have to analyze that. And we are a core team of 6 people and a dog who's barking too much today.
The dog is helpful, actually.
And so this is done by a computer. Some AI-based algorithm help as well. And we basically do all this analysis mostly with a computer, automatically. Then after we go back into the details, and that's what you're gonna basically do in the next 2 weeks, is to go through the details.
Probably the next month I'm going to be doing this. So we had that July observation, then we had another one just a few days ago, and we've got 2 more windows to observe. So
do you want to show that?
Yeah, I'll show that.
So who else can observe this? Everybody?
It's truly worldwide. It's another worldwide opportunity. So the window, like I said, is about 22 hours and passes over most locations on Earth. In this video, you can see by the red area is an area of visibility. So when that red area passes over your location, you will be able to see the target. So this is truly worldwide, and it's going to be the end of next week for us. So it'll be August 23rd and August 24th. We'll have 2 chances back to back to see this.
So put that in your calendar. Before we don't leave that, someone asked what's the name of the planet. It's on the top here.
Yes, and it's
BD +054868 AB.
Yep, it's in the constellation Pegasus.
And we're gonna make a song about with this name. It's so pretty.
We should.
Another question we have. So is this disintegrating exoplanet a remnant core of a giant planet, or it's a terrestrial planet?
We think that it's just a terrestrial planet.
Okay. So, but spectroscopy, meaning the analysis of the light, of the fragments and the tails, will probably give us some indication of the composition of the core, if it's a core, or the composition of the planet. So we'll be able to understand this better by doing this analysis.
Exactly.
But for that, we need to have the context.
Yeah.
That's what we're providing with this network of small telescope and our citizen astronomers.
Yeah.
So thank you very much to all of you who watched that, who watched the transit and recorded it. We will have pretty soon a nice like her. Right?
Yeah, I'm really excited.
She has a lot of pressure. She doesn't realize.
I do.
There's a lot of pressure.
It's a lot. It's all right though.
All right. We good with the exoplanet? Remember, if you have any questions, you should ask them. Look at the questions. We may take sometimes to talk about UFO. Yes, omnipotent media wants to talk about UFO. We will talk about that. But before this, let's talk about Pulcova, an asteroid in the main belt. It's a 100-kilometer asteroid in the main belt. There is like 200 of those. Okay, so we know a lot of those. We know a lot of those asteroids. But we don't really know much about the asteroid itself. Like most of the time, we have a rough idea of the size, of the shape. So what we can do to get a better understanding of the asteroid itself is to send a spacecraft over there and take pictures. It costs money, takes a lot of time, and very few people can do that. The other way is to wait for this asteroid to pass between us and a bright star. That's what we call an occultation. Mm-hmm. So if you look at an occultation, contrary to a transit, what you see, the star disappearing, okay, in this case. And basically, if you can imagine that you see the shadow of the asteroids on the surface of the planet, and it's moving as the planet Earth is moving with respect to the star and the asteroid. And this can last a few seconds. So we have an asteroid, Pulcova, that was discovered a long time ago, I forgot exactly which year, that will occur on October 26th, on August 26th, so in 12 days, 11 magnitude star. We can show the path of this occultation. The reason it's interesting because it's an occultation that crossed the entire United States, from San Diego, roughly area, all the way to, I think it's Maine or New York, something like that here. So if you locate it in the path of the occultation, you will see the star disappearing for around 8-10 seconds. Okay, and if you have multiple people observing this simultaneously, we will be able to have the silhouette of the asteroid. So see the shape of the asteroid, because we see the shadow, remember. More importantly, several years ago, Bill Marline and a group at the CFHT, the Canadian Far-Wide Telescope, discovered a moon around Pulcova. The moon has no name yet.
It has a name, but it's real ugly.
Yes, S2000 7621. That's
almost as nice as the planet.
All right. So this moon, you can stop the video, but leave it, sorry, because this moon is away from the primary, from the large body. It's smaller, it's a few kilometers in size. So this moon will also occult the star. It will last only 1 second, roughly. We have an idea of the size of the moon. We believe it will last 1 second. So if you are located not on the path of the occultation, but slightly away, you should also observe it, because maybe you will see the blackening of a star, and this is due to the presence of a moon. So we gotta confirm the location of the moon and know the size of the moon thanks to the observation. How cool is that?
I think it's pretty incredible, just what we can gather from a rock blocking a star for a moment. That's the most incredible thing about science to me, is what we can extrapolate from just a little information, and now the fact that we get to have so many people involved. So definitely check out our website. It's science.unistellar.com. You can find the prediction for this path on August 26th and plan your observation of it. It's going to be really cool.
Yeah. And if you're not yet on our Slack, please join our Slack. If you're a telescope Unistellar user, you just register. You create an account on the app, and then you go on our website, you log in on your account, and then you follow the instruction, and you become a citizen astronomer. And we have a nice community of 3,000 people talking to each other and helping each other. Okay. We have a lot to talk about, but we're reaching the end of our.
Maybe we take some questions.
Yeah, I've been taking some. In fact, in the conversation, Presto Pimiento, we answer to your question. Michael Nelson, we answer also to your question. What about waiting if there is more questions? UFO. I'm getting bombarded by emails and text messages from friends, family members about 3i Atlas, because apparently there is some people who have been writing that this is a spacecraft of a UFO and other ideas. Okay, so let's be very clear here. We have observed this body. We saw its trajectory. It's follow basically the Kepler law. Okay, I mean he's not perturbated so far by anything. So it means he doesn't have his own propulsion system. Yeah. The shape, the image taken with the Hubble Space Telescope that was taken like 2 weeks ago, a week ago, clearly show a comet-like appearance. And we show today that the profile, the brightness, seems to also follow what we expect for a comet. So, as a human being, if I give you all this information, the likeliness of this being a comet or comet-like body is extremely high. Okay, and that's the way science works. I'm not claiming it's a comet. I'm not claiming it's an asteroid. I'm not claiming it's something else. I'm not writing papers about something else because I don't need to. Because at the moment, what we see is that it behaves like a comet. So we are doing studies of this body to confirm it's a comet and see emissions. Right now, we have seen a lot of gas, a lot of dust, and gas start also appearing in the spectrum. So scientists are kind of confident that this is a comet. Papers are being published live, and you can just look at them on AstroPH, on the archive if you want, or you can also look at articles published by some great journalists explaining, like Sky and Telescope is a very good article, explaining what we know about this comet at the moment. Then you can take the other side if you want, like reading endless paper written by one person only that claims something that people seems to believe is true. A few of us believe it's true, and talk a lot about this one. But the general consensus is that this is a comet, and it's interstellar comet coming from another solar planetary system. And we are working on studying, understanding this as a phenomenon. Okay, that's the way science works. We don't make assumptions and then write papers or bend the rules or the law, so we prove that our crazy assumption is true. I'm gonna be a bit excited by this here.
He's getting passionate.
But that's not the way science works. Science is you take facts and data, and then you have a theory, and you disprove your theory. The data are what matter first. It's not your crazy idea. People can think what they want. It's great to have crazy idea because I think it's important to be creative and to also think outside the box.
Absolutely.
But I don't need to go on TV to say crazy stuff. And I think scientists should stop doing that if they really believe that's the way science should work. But we can talk about that another time.
We have another little bit of news that's maybe not so emotionally charged, because I don't think we have any more questions, but if y'all have questions, we have time to take a few more. But while you're thinking of those questions, we can talk about the new potential planet that was discovered around our closest star system with JWST. So it's pretty cool.
That's a very cool result. I mean, this is the way, this is a clear demonstration of how science works and how we make progress step by step. Alpha Centauri, closest planetary system in our to us, 2 light years away from us.
Yes, three planets, 3 stars.
3 stars. Yeah. 2 G-type stars like G and F orbiting around each other in 80 years or something like this, and a very distant brown M-type star, very far away. So what scientists they've been observing this system for quite a long time because it's the closest to us, so it's the easiest. And in 2009, we used the 8-meter plus telescope, the VLT, and someone detected something interesting around it, a tiny dot that seems to be moving. It could be an artifact They were not sure at the time. It was done with an adaptive optic system, so a very powerful instrument. JWST, the Hubble Space Telescope, the James Webb Space Telescope, observed it also in 2024 and 2025.
Yes.
And they saw something too. And when I say they saw, it's 2 papers with a lot of data analysis, very rigorous simulation and so on. But they have seen some features nearby the star, very faint, 10,000 times fainter, I think, or something like that, than the star, at roughly 1 AU from Alpha Centauri
1 to 2 AU.
Yeah, 1 to 2 AU.
From the brightest star in the system.
And this could be a Jupiter size or Saturn size exoplanet around Alpha Centauri A. And I think this is cool. And it's cool because they observed it in 2019 from the ground, 2024 from using JWST. They did not see it in 2025. There are 2 observations. They did not see it. So they're not claiming they discover an exoplanet. They say we have an exoplanet candidate.
Yeah.
And the reason they believe they did not detect it in 2025 is because it was due to the inclination of the system. The planet was too close to the star to be detectable because it's very faint compared to the star. And if we need to use this technology called coronagraph to see the planet, and if the planet is behind the coronagraph, then you don't see the planet.
Right. And a coronagraph is essentially just blocking out the light from the star so that the planet can actually be seen. So if it's behind the star, you're not going to see anything.
So, exactly. So what you do in this case, you just wait. You're patient. Patience. Something that apparently people have a hard time understanding, that we as scientists, sometimes we have to be patient. So we wait, and in a year, probably even less, this star, this planet, if there is a planet, should be outside the coronagraph of JWST. They are going to observe it again, and if it's confirmed, then we may have discovered
the closest planet in the habitable zone of a star.
Is a star.
Even if it's a gas giant, it's still pretty cool.
And you know what I like, if it's a gas giant, is because maybe if he has moon, and maybe
you do
the
love
moon,
moons.
and maybe the moon,
moons.
it's all about moons, and maybe the moons as habitable, and maybe in this habitable moon because there is liquid water, there is an ocean, or there is some kind of life.
Could be cool.
That's a cool part of this discovery.
I agree.
There is Pandora is basically that from the movie Avatar. It's the moon around a Jupiter-sized exoplanet in the Alpha Centauri system.
It comes full circle. Love it.
So maybe science fiction was not fiction.
Well, we're kind of in the era of some things that used to be science fiction becoming actual science and reality. So it's a pretty neat time to be alive and to be a scientist. I think, did we have one more question?
We have a question from Anand.
Let's see.
Anand asked if the 3i has any difference compared to Comet we see generally. It's a bit too early, but there is some interesting result that show that it's a very dusty planet compared to the dusty comet compared to the comet we see in our solar system. And that may be due to the fact that it's drier, because it may come from a planetary system which has less water. So that's the kind of research that we do with this interstellar body. We can understand better the composition, bless you, of this planetary system. But that's something that I think it's just been published. It's not even accepted yet for publication, but that's an interesting result. Do we have anything else to talk about?
I think that's it. I think we covered it.
So many things already.
Thank y'all for your great questions. This was super fun. And so as you heard, we have a couple of really cool observation campaigns, opportunities coming up towards the end of the month. So August 26th for the asteroid Pulcova, if you are in the path that goes across the United States, and everyone around the world in our global decentralized telescope network. If you have clear skies on August 22nd or 23rd, give that disintegrating exoplanet a shot. And you'll see a lot more about that on our website.
And it will be an amazing way for us to do great